In active conflict zones, some of the highest risk to life occurs before the unit reaches the objective. During transit, steep, claustrophobic mountain passes create ideal conditions for an ambush, making the road as dangerous as the front line. Standard transport trucks move troops efficiently, but their light-skinned construction offers little resistance to high-velocity gunfire or the immense upward pressure of a hidden IED. Addressing this vulnerability required a shift in domestic engineering, an effort supported by Ratan Tata's vision to bridge the gap between heavy industry and national security needs. The result is a specialized transport designed for the Indian Army, a vehicle built to function as a reinforced moving shield, protecting the unit during its most exposed phase of movement. Engineering this level of protection requires solving three problems at once: stopping ballistic projectiles, surviving an underbelly blast, and insulating against concussive force. In modern conflict zones, success is no longer just about getting from point A to point B. It's about arriving with the unit's combat effectiveness fully intact. The first line of defense focuses on the perimeter, neutralizing the kinetic energy of rounds fired at close range. When a high-velocity projectile strikes the outer composite armor, the kinetic energy is flattened and dispersed laterally, preventing it from punching through. Because ambushes involve automatic fire, the reinforced structural backbone holds these layers in place through multiple hits, preventing the wall from buckling. While this secures the sides, ballistic armor alone does not account for threats hidden beneath the vehicle. True survivability in these zones requires an additional layer of engineering, designed to manage the undirected energy of an explosion from below. This simulation illustrates an IED detonation. The shock wave expands violently upward, delivering a massive amount of undirected energy against the center of the vehicle. On a flat-bottom truck, this force has nowhere to go but up, which can toss the vehicle and crumple the chassis instantly. The Tata bus uses a geometrically angled undercarriage. The V-shape physically slices the upward force, redirecting the blast wave outwards. But even if the hull holds, the acoustic shockwave can pass through the frame, causing lethal internal trauma. Internally, the bus features secure compartments, structurally isolated from the main frame. This decoupling helps shield the troops from the violent acceleration of the blast. Finally, the seating and the reinforced flooring use a shock-absorbing structure, acting as a physical buffer, dampening the final wave of energy before it reaches the soldiers. By prioritizing the intelligent deflection and dampening of energy over brute weight, the design focuses survival on the most critical payload, the soldiers themselves. When individual survival rates increase, the tactical options available to commanders on the ground also expand. Higher thresholds for protection during movement allow for deployments through high-risk transit routes that might have previously been avoided due to the high probability of ambush casualties. This shift is the result of domestic engineering addressing a specific military need, applying industrial technical strengths to solve a persistent security problem. By mitigating the impact of IEDs and small arms ambushes, these vehicles challenge the effectiveness of asymmetrical tactics used by hostile forces in mountain regions. Protecting the soldier during the transit phase preserves the unit's strength for the mission ahead. How do you see this focus on armored transport impacting the way units move through high-risk zones? Tell us your thoughts in the comments, and follow for more tactical breakdowns.